Alright, in this video we're going to finish up section 2.6, function composition, and that's what we're going to start with right here, composition of two functions. Another way to combine two functions is to form the composition of one with the other. For instance, if f of x is the x squared function and g of x is x plus 1, the composition of f with g is f of g of x, which is f of x plus 1, or x plus 1 squared. If that's a little confusing, maybe this will explain a little bit better. We're going to take this g function in its entirety and plug it into the f function. So here's my g function. I'm going to sort of wrap this up like a Christmas package, and I'm going to plug it into the f function wherever I see an x. So I'm going to take this as a quantity and plug it in for that x. So instead of being x squared or something squared, it is this quantity, x plus 1, quantity squared. And this composition is denoted as f compose g. You know, f times g with the little colored in dot, f times g is different from that open circle, and that's read as composed. F composed with g. So what's the definition of the composition of two functions? The composition of function f with the function g is f compose g of x, or f of g of x. G of x is the inner function that is going to be run through the outer function f. The domain of this composite function is the set of all x in the domain of g, such that g of x is in the domain of f. And you know, the domains of these can get a little tricky. We'll cross that bridge when we come to it. But graphically, I like this little picture down here. This shows sort of what we're doing. We have two functions, the g function and the f function. So we're going to take an x value from the domain of g. Here's our g function. This is its domain. We're going to plug an x value into the g function and get the output g of x. G of x is in the domain of this other function f. You know, this light blue circle in the middle, this is the range of g, but it's also the domain of f. So this g of x, we're going to put that into the f function and get an output over here in f of x's range, f of g of x. So it's sort of like a two-step process. We take an x value, we plug it into g, and we get to the middle. We take that output of the g function, plug it into the f function, and that takes us to the final range of f. Or what we can do is sort of like a shortcut. We compose the functions together. F composed with g. We put this x value right into the composed function, and it skips that middle, that domain of f or the range of g, and takes us right to the final range. So let's see what we have here. Example 5, the composition of two functions. Given f of x is x plus 2, and g of x is 4 minus x squared, find the following. F composed with g, g composed with f, or g composed with f. We're going to evaluate that at negative 2. So let's do the first one here. Let me switch, this will work. For part A, we want to find f composed with g of x, or I like to write it as f of g of x. Because here we can see that the g of x is the inner function. The inner function is going to be run through the outer function. So my inner function here is g of x. That's this g of x. I'm going to wrap this g of x up like a Christmas package, and I'm going to plug it in right there into the f function. So the f function, f of g of x, the f function was x plus 2. But I'm going to take out that x, the x plus 2. I'm going to take out that x and replace it with the whole inner function. My inside function here is g of x. So I'm going to take this g of x function and plug it in the place of the x in the f function. So this becomes 4 minus x squared plus 2. And f of g of x is equal to, I can disregard the parentheses because we're adding. 4 plus 2 is 6. 6 minus x squared. That is my composed function, f composed g of x. Okay, for letter B, I'm going to flip it around. I'm going to do G composed with f of x. So for letter B, we're going to do G composed with f of x, or G of f of x. Now, f of x is my inner function. My f of x function will be wrapped up like a Christmas package and plugged into my g function. So I'm going to take this f of x function, x plus 2, and I'm going to plug it in for this x squared. So this was 4 minus something squared. Now that's something. That x is going to be replaced with this quantity, x plus 2. So I'm going to have, my g function was 4 minus x squared, or something squared. Now that something is the entire other function. I'm going to take this x plus 2 and plug it right in. X plus 2 quantity squared. So this is g of f of x. And let's FOIL that out. We're going to have 4 minus, and then when we FOIL out this function, x squared plus 4x plus 4. And then we can distribute the negative. If I distribute the negative, x squared becomes negative. This 4x becomes minus, and this plus 4 becomes a minus 4. So now we can, oh, that's just ugly. Let me just do this right. And let me sneak up here. 4 minus x squared minus 4x minus 4. I just distributed the negative, and now I can collect like terms. We'll have our squared term first, negative x squared minus 4x, and then we have a plus 4 and a minus 4, which canceled. So there's our final answer, negative x squared minus 4x. And let's see, I think this is the one. Yeah, this is the one. G compose f. Let me get a little of this garbage out of the way. So our G composed f of x is what we just found. G of f of x was equal to negative x squared minus 4x. And here in part C, they want us to just take that composed function and put a negative 2 through it. G of f of negative 2 is going to be, now watch our negative signs here. Our function is negative something squared minus 4 times something. Now that something is a negative 2. So here, negative 2 quantity squared. Negative 2 times negative 2 is positive 4, and then this negative comes into play. So that's a minus 4. And here we're going to have a minus 4 times negative 2 is negative 8, minus a negative 8. So that's going to turn into a plus 8. Minus 4 plus 8 is equal to a positive 4. Okay, and I see up in the upper right corner there's a blue box. What's this about? Okay. The following table of values help illustrate the composition in this example. So we have our g of x function. That is 4 minus x squared. Well, when I plug in a 0, 4 minus 0 squared is 4. 4 minus 1 squared is 3. 4 minus 2 squared is 0. 4 times... what was I doing there? 4 minus x squared. Oh, if x is 3, we square it 9. 4 minus 9 is negative 5. So here are the table of values for g of x. And then these outputs become inputs into the f of x function. So when we plug these into the x plus 2 function, 4 plus 2 is 6. 3 plus 2 is 5. 0 plus 2 is 2. Negative 5 plus 2 is negative 3. If we do the composition, f of g of x, we take this beginning input and we jump right to the final output. In goes a 0, out pops a 6. In goes this 1, we jump right to the end, 5, 1 to 5. We put in a 2, out pops a 2, 2 to 2. Plug in a 3, out comes a negative 3. The composition of the function allows us to sort of jump over this part. We go right from the beginning input to the final output. Note that the first two tables can be combined or composed to produce the values in that third table. Okay, now this part can get a little confusing. We're going to talk about the domains of composite functions. And let me just sort of sum it up like this. We're going to be doing this one, f compose g of x, f of g of x. When it comes to the domain, consider two separate domains. Consider the domain of g of x, or the inner function. Consider the inner function's domain. So we consider the inner function, just whatever g of x is, before we compose it. And then we're also, that's number one, we're also going to consider the composite domain, the final composite function's domain. Consider f of g of x's domain. So we're actually going to look at two domains and see where they overlap. Where that overlap is will be the domain of the entire composite function. So let's check this out. Here's f of x, here's g of x. We want to find f compose g, or f of g of x. We're going to take the g of x function and run it into the f function. So here's my g of x function. I'm going to wrap this up like a Christmas package, and I'm going to plug it into my g of x function, or my f of x function, wherever I see an x. You know, f of something, f of x, was that something squared minus 9. So all I've done is sort of replace this with a placeholder. F of something was something squared minus 9. Now I'm plugging the entire g of x function into that spot. And our g of x function, g of x, was root 9 minus x squared. Root 9 minus x squared. So when we start to simplify this composite function, f of g of x, the square and the square root cancel. So we're left with what's under the radical, 9 minus x squared, and then we have our minus 9 at the end. The 9 and the negative 9 will cancel, so it looks like our composite function is just negative x squared, because these have canceled off. So if you look just at the final composite function, and we start considering the domain, we're going to think, okay, the domain of the composite function, f of g of x, that is all real numbers. You know, negative x squared, there is no division that we have to worry about dividing by 0. There are no radicals that we have to worry about keeping positive numbers under. So we're going to think for the composite function, all real numbers. But we don't just consider the final composite function domain. We also have to go back to the inner function. Here our inner function was this radical, the square root of 9 minus x squared. The square root of 9 minus x squared. Remember, when we have something under a radical, we always want that to be greater than or equal to 0. Oops. There we go. So here, if we square both sides, we get 9 minus x squared greater than or equal to 0. Or add x squared to both sides. 9 must be greater than or equal to x squared. So if we square root, we get a plus or minus 3. Plus or minus 3 must be greater than x, or another way just to think about that is x is stuck between 3 and negative 3. If I plug 3 or negative 3 in for this x and square it, I'm going to get a 9. 9 minus 9 is 0, and that's as low as we want to go. So any number bigger than 3 or less than negative 3, when we square it, will be greater than 9 and will result in a negative underneath that radical. So the composite function was all real numbers. Our inner function, just the g of x, that domain was negative 3 to 3. And still to this day, when I think about the composite function's domain, I think about the number line and any overlap. So for the first one, the composite function, this negative x squared, that was the whole real number line. That was all real numbers, so I'll just highlight that in blue. For the g of x function, we're restricted between 3 and negative 3 with the endpoints included. So I imagine there's brackets at 3 and negative 3. Where do the red and blue domains overlap? Well, out here the blue is all by itself, so that's gone. Over here the blue is all by itself, that's gone. The domain of the composite function, f of g of x, is going to be from 3 to negative 3. Even though the final composite function looks like it would be all real numbers, you always have to go back and consider that inner function's domain. A couple problems for a practice. Now here's a little twist. We really didn't do anything like this in class, but we'll get through it working on the huddle and wrapping it up at the end of class. We're going to do F compose G, G compose F, and G compose G. That's sort of like, here's our G function, x to the third plus 1. We're going to take that function as a package, wrap it up, and plug it back in where we see the x. So that x right here is going to turn into the quantity x to the third plus 1 to the third power, and then we'll have our plus 1 on the outside. For number 43, you're going to compose it both ways and come up with the domain. And those domains can be a little tricky, so pause the video, try those problems, come back and see how well you did. Alright, number 39, we're going to do part A, F compose G, or F of G of x. And that's telling me I'm going to take the G function as my inner function and put it into the F function. So my F function, F of something, was equal to the third root of something minus 1. I've just rewritten my F function with a placeholder. F of something is the third root of something minus 1. Now that something is going to be the whole G of x function. So I'm putting the G of x function in there. And G of x is x to the third plus 1. So underneath the radical, we can do a little simplifying here. We're going to have the third root. The plus 1 and the minus 1 will cancel, and we're left with x to the third. Ooh, that's nice. What is the third root of x to the third? Well, those third and third roots are going to cancel, and we're just left with good old x. Okay, let's try letter B. B is G compose F. G of f of x. So the G function was x to the third plus 1, or something to the third plus 1. Well, now this something is the entire f of x function, and f of x was the third root of x minus 1. Wow, well, you look at that. We have a third root to a third power. Those, of course, are inverse operations, so those are going to cancel each other out. Our G of f of x is third and third root cancel. We're left with x minus 1, and then our plus 1 at the end. So the plus and minus 1 are going to cancel, and again, we are left with x. Neat. We did the composition one way and got x. We did the composition the other way and also got x. That tells us that these are actually inverse functions. If I take an x value and plug it into f of x, I'm going to get an output. If I take that output and plug it into the g of x function, I'm going to get right back to where I started, the original input I put into the f of x function. Last one, C, G compose G. G of g of x. So that tells me I'm going to take the g of x function, which was something to the third plus 1, and I'm going to replace that with the entire g function itself, x to the third plus 1. Now I guess we know how to FOIL out those binomials to the third power, and then we could add 1 to it, but I think it's much easier to see, as a simplified function, just to leave it alone. Alrighty, that's it for number 39. 43 is where they're asking us about the domains, and historically this is where, this gets a little confusing. So we have f of x is x squared plus 1, g of x is the root of x. For part A, we are asked to find f compose g, or f of g of x. So I'm going to take the g function, wrap it up like a Christmas package, and plug it into the f function for that x. So instead of something squared plus 1, I'm going to have this in the place of that something. So we had something squared plus 1. That is our f of x function, something squared plus 1, and now we're plugging the g function in to the f function. So here, the square and the square root are going to cancel, and our composed function, f of g of x, is x plus 1. Now they're asking us for the domain. Remember, we first look at the final function. The final composed function here, x plus 1, that's just a linear function. So the composed function is all real numbers. But we have to go back and look at the inner function. Our inner function here was the square root of x. G of x was the inner function. What restriction does the square root of x have on a domain? Well, that x must be greater than or equal to 0. So if we think about the overlap, here's our number line. The set of all real numbers is the whole number line. And the second restriction, our inner function's restriction, is x must be greater than or equal to 0. So where those domains overlap is the domain of the composite function. So for f compose g of x, our domain is going to be x is an element of the real numbers such that x is greater than or equal to 0. Positive numbers only. Now let's see what happens when we reverse that composition. Now we're going to do g compose f. G of f of x. And we're going to take the f function and plug it into the g function. So the g was simply the square root of x, the square root of something. Now that something is x squared plus 1. And it looks like that's as simple as we're going to leave it. We can't combine or eliminate anything underneath that radical. So I guess it stays just like that. So now we think about the domain. The domain of the composite function, since it's a radical, we have to have what is under the radical, x squared plus 1, must always be positive. And because we are squaring something and then adding something to it, that is always going to be positive underneath the radical. So for the final composed function here that we're looking at, we can plug in any number for x. If it's negative, we're going to square it and it will be positive, and we'll add more to that so it will remain positive. So for the first part, for the final composed function, it looks like all real numbers. And then we got to go back and look at the inner function. Here our inside function was f of x. F of x was this simple polynomial, x squared plus 1. The domain of that is also all real numbers. So where do these domains overlap? Well, everywhere. Our final composed function, g of f of x, is all real numbers. The assignment to finish up this function composition, it's just 3 problems, but you're doing, you're composing f of g of x, g of f of x, and maybe g composed with g. And they might be asking you also to look at the domain. So slow down. It's only 3 problems. Take your time on them, especially when you're thinking that domain through. And I'll see you in class tomorrow.